Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 10, Atomic Structure and Periodicity, Part 3. In this video, we're primarily going to be talking about quantum numbers, what they are, what they mean, and how we assign them, which you might not have seen before. Pause here. So before we get into quantum numbers, we're going to start by describing an orbital. This is really the only definition I'm going to ask all year that you memorize word for word. An orbital is a mathematical function that describes the wave-like behavior of one or two electrons. More on the one or two part later on. For now, just think of it as it's describing one or two electrons. So we know that electrons have both wave-like and particle-like properties. When we are describing their wave-like properties, we might want to describe them mathematically, what they look like. So you may have seen something that looks sort of like a circle or that looks sort of like a dumbbell in your prior science classes. Those are really just mathematical functions that describe where that electron might be. And I say might be because I'm describing the wave-like behavior. The actual location is not 100% known. And then the orbitals of electrons are going to be best described by their quantum number. So it's just four numbers that are giving some information about that electron. Let's get into the four numbers. Pause here. So the first quantum number, I think, is the easiest one to understand. It is just the energy level of the electron. So the principal quantum number is n, and that can range from 1 to the row number that the element is in. So for example, hydrogen can only have n is equal to 1, or at least in the ground state, more on the ground state a little bit later on, whereas something that is higher up on the periodic table, say something in the third row, can have n is equal to 1, n is equal to 2, or n is equal to 3. Pause here. So the second is the azimuthal quantum number. That describes the shells or the shapes that are available. So that would be either the S, the spherical, the P, the dumbbell, the D, the clover, the F, the double clover, which we're going to get a little bit more into in a later video. And the L can always go from 0 to whatever n is minus 1. So if, for example, an electron is in the n is equal to 3 state, then L can be 0, 1, or 2. If an electron is n is equal to 2, then L can only be 0 or 1. Pause here. So then once we know the n and the L value of an electron, there's also something called the magnetic quantum number, which describes the specific orbital within the shell. So oftentimes within a specific shape, there is more than one orientation of the shape, and the values of L dictate what that shape is. So if, for example, n is equal to 1 and L is equal to 0, because m sub L can go from negative L to positive L, m sub L also has to be equal to 0. Well, if you didn't already know, when I'm saying m sub L, what I'm saying is an m, it's subscript L, S-U-B-L, so m sub L just means m with a subscript of L. Another example would be, let's just say n is known to be 3, L is known to be 2, then m sub L could be negative 2, negative 1, 0, positive 1, or positive 2, meaning there are 5 different values of m sub L in that case, which will correspond to an area of the periodic table that I will show you in class. And then pause here, it's the last one. So when we discuss something as being spin up or spin down, it doesn't really have a whole lot of meaning in terms of actual spinning of the electrons. The way I think about it is that the spin quantum number accounts for the fact that I can't have two electrons in the same place at the same time, and m sub s, so m with a subscript of s, helps us account for that. So it's always going to be either positive 1/2 or negative 1/2 for an electron. For other particles, the m sub s values can be different, but for an electron, it is always positive 1/2 or negative 1/2. So the best way to get all this information is to look at examples. I know that it is common to be a little bit confused by it the first time that you see this. Let's take a look at an example. Pause here. All right, I'll work through this. So n is equal to 1, that is allowed. L is equal to 0, that is allowed because n minus 1. M sub L is also allowed. M sub S looks allowed, so this one is permitted. Then the second one, n is equal to 2, L is equal to 2. This one is not allowed because L must be less than n. So then I see n is equal to 3, okay. L is equal to 1, also okay. M sub L is -1, M sub S is +1/2. This is permitted. And then we'll take a look at more complex examples in class. It's not really the kind of example that merits a video. Pause here. So that brings me to the Pauli exclusion principle, which just states that within the same atom, no two electrons may have the same 4 quantum numbers. So if you know, let's say that you've got an electron that is in n is equal to 3, L is equal to 2, L is equal to 2, M sub L is equal to +1/2, then there cannot be any other electron within the atom that is able to have those same quantum numbers. More on that a little bit later. Thank you for watching and have a great night.